So hello everyone, I'm Katherine Rocha, and today we're going to be talking about design trends. And so this is going to be super interactive, so there are room mics here. And so basically what we're going to be doing is looking at different design trends and figuring out, is the new thing actually cool, or do we need to reevaluate it and maybe we should be using the old thing? Cool. So a little bit about me. I'm a software engineer at Atomo Space in Broomfield, Colorado. We're working on orbital transfer vehicles, and we have 2 spacecraft currently up in space running C++20, so we're currently doing some really interesting things. Before that, I worked in a really old code base, over 20 years old, luckily using C++17, but in a code base that old, you're gonna end up not actually using all of C++17. So still dealing with a lot of macros, a lot of object-oriented programming. And so I learned a lot through that experience, and that kind of influences that idea of looking at design trends. So yeah, and then if you know anything about me, I'm kind of a software historian or genealogist. I tend to look at that big picture, take a couple steps back and try and understand the why. And so a lot of what I've looked at is why are we doing the things that we're doing, and how can we do the things in the future a little bit better? So my initial discovery here is that kind of looking at the past. So we look at a really good example is like water bottles. If you look at it, like everyone had a Stanley Cup a couple months ago, and now we're moving forward and looking at it and like maybe that's not the cool new water bottle, but like Hydro Flasks were the cool new water bottle a couple years ago. And so maybe we're doing the same thing with our source code. Maybe our code is, oh look, here's a stood pair. I'm gonna use a stood pair everywhere instead of actually not using a stood pair because you really don't need one, but it's kind of cool looking. So yeah. So we're gonna try and look at it and take the new patterns and look at them with the same scrutiny as the old one. So instead of going, oh, this is a cool new thing, maybe let's look at it and see, is it actually cool, or are we just thinking it's cool because it's a new coat of paint? Cool. So this is kind of our investigative process for this. So what we're gonna do is we're gonna kind of look at a generalized timeline, try and figure out how everything went together, what's kind of going on, and then we're going to look at the original trend, try and understand why did the original trend happen, what was the original trend trying to do, and then we're going to look at the new trend, try and understand kind of what it's trying to accomplish, what it's trying to do, and then we're going to also look at the code for each of those in order to be able to take a couple steps back, look at the code and go, is the new one actually better, or are we inserting, let's say, so much template metaprogramming that it's actually really hard to read and it's causing a lot of readability issues? Or is it actually helping a lot and making it really easy to read and simplifying and making things clear? So we're gonna do that analysis and try and figure it out together. So as I said earlier, this is gonna be an ultra interactive talk, and we're gonna kind of parse through this together as a group in order to figure out kind of what's best and what actually is good and what actually is bad. Cool. So our first one is global interfaces and global state. So first is our use cases. So we have kind of 2 different buckets here. We have our global interfaces and our global data. So for a global interface, think of things like logging, external I/O. Our goal is to be able to connect to something else and be able to deal with that interface. And so this is kind of our quintessential need for a global, because we don't actually want to be able to have 18 different copies of our logger accessing the same file I/O. We want only one copy of that. We also deal with that for a lot for resource management, no matter what that may be. And then for global data, we do that a lot with like initial parameters. Be it you're reading an XML file with all of your initial data, or passing in something, that initial parameter is something that may be stored as a global that gets passed around everywhere. We also may use it for things like state parameters. So I work in the aerospace industry, so dealing with position, velocity, and acceleration are things that are really common. And those are things that you may end up passing as a global in order to deal with that, because it's easier for everyone to access the same data than to worry about making sure you're passing it correctly through all these different areas. Cool. So here's kind of our timeline. So we've got our global variables first, our quintessential like C-style global variables that you can kind of access everywhere, thinking more of like your micro-embedded sort of application. And then we're gonna move into the design pattern singleton. So this is the book by the Gang of Four. It's kind of your quintessential object-oriented book about design patterns. And in that book, there's a description of what the singleton actually is and how you actually use it. And so this is kind of what I think of as your original singleton. And then we go to the Myers singleton, and then monostate, and then dependency injection. Cool. So our singleton, basically what's going on with a singleton is we want to be able to hold one copy of all of our data and functions and allow everyone else to access it. Think of your like get instance function or instance function. Who here's used a singleton? Cool. Who here likes using singletons or thinks they're really great? Okay. Who here still sees a need for singletons? Cool. So with that, we're going to see if maybe we can get away from a singleton or maybe we're stuck still using a singleton. So does anyone have any ideas of what are some of the nice things with a singleton? What are some of the things where you're like, wow, this is awesome? Yeah.
Control some things are initialized.
Okay. Anything else?
Not so many setters.
Yeah, not so many setters. Yeah.
You can kind of avoid copying sometimes or like moving things around a lot.
Avoids a lot of copies. Yeah.
Same upsides as global, you don't have to thread a parameter 50 functions or something like that.
You don't have to do the parameter threading. So with that, we have that easy access and it's really identifiable. But with that, it's also really hard to test. And so with that, because everyone can access it, you get unintended side effects of someone being able to access your singleton and do things with it. So it's really hard to be able to test it and make sure that you're getting the outputs that you expect. And I feel like based on everyone's feedback, it's kind of quintessentially overused. There's this idea of maybe we shouldn't use it because we use it everywhere. Cool. So here's our first two. So on the left, we have our first singleton, and we're doing a plotter here. So we're accessing a plotter, and we're going to plot from that plotter. So we're going to call get instance, and in get instance, we're going to then be able to plot and send data to this plotter, which is this shared global interface. Cool. So the left one is the design pattern singleton, and the right one's the Myers singleton. So is there anything interesting anyone sees about these or thinks maybe is good or bad?
The Myers singleton makes use of like intrinsic language guarantees about like thread safety with statics, whereas the other one is kind of trying to hack it together.
Yeah. So the right one has thread safety, and the left one really doesn't. Yeah.
Nothing that controls when the singleton is destroyed.
Yeah. So we're really hoping the OS keeps everything okay, and that when the file ends up, or when the program ends up ending, hopefully we'll clean up that memory and everything will all be good. And so it's kind of what we're relying on for the left, the design pattern singleton. Yeah. Cool. And then if you notice here, the left one also is a lot more older style syntax, and the right one is a little bit more modern, and so it's enabling us to do a little bit more. Cool. So then what we're going to do is, maybe we aren't the biggest fan of this singleton, but we have to do it everywhere, and so we're getting a little tired of doing all this copy paste, and so we're going to make a wrapper and be able to wrap our singleton class everywhere we want to wrap it. So right now we're kind of processing through our original code and seeing how we're making it better throughout time. And so this is kind of our next step forward. And so we're going to have this template class, and we're going to wrap our singleton in it, and so that way whenever we want to have a singleton of any class, we can just make our own singleton, and we don't have to worry about making this singleton, making sure someone's returning the instance correctly, and making sure it's okay. If you notice, we're also returning a reference, which is really cool because we're no longer dealing with that raw pointer and hoping everyone else gets the raw pointer right. It also reduces one character, so you're doing a dot instead of an arrow. So if you're looking at your line length, it kind of helps there. Is there anything anyone sees about this one? Yeah.
What's the point of the private default constructor of singleton?
So that's to ensure that no one can actually create a singleton class. Yeah.
You also have a disabled copy.
I have not. So I'm trying to fit it on the slide, but yeah, for sure. Hopefully the constructor gets it across. The idea is that we're trying to have that one access. Yeah. Yeah.
This may have been the case in all the previous slides as well, but why is the get instance returning the mutable reference to the singleton here?
So you're ending up returning the reference, but you're calling functions on it. So you're going to end up modifying the underlying data.
Why should you be allowed to do that from anywhere you can call, that from anywhere in the code base in any thread?
I mean, that's the fun of a singleton, right?
It depends on the application. Sometimes it needs to be mutable, sometimes it shouldn't be mutable.
Well, yes. Why though? Why add that complication?
Yeah.
I mean, at least with this wrapper, you could just say a singleton of const whatever.
Yeah.
True. I think my issue is more like because this is an abstraction on the idea of a singleton, the thing that the singleton is wrapping may or may not have an idea of thread safety. And nothing about that singleton really, nothing about this generic here lets you kind of control that.
So you are controlling it, but at the same time, you're making it so that way you don't have people returning a raw pointer. So you are kind of controlling some portions of it, right?
Well, you know that the pointer's not null. You're not working with a null thing, right? But like, the thing that you're wrapping, that T, what constraints are on that T?
Yeah. So
Should it be a singleton? Right? This is making it easier to make a singleton, especially if the underlying like constraints on that type are not valid.
So we are carrying a lot of risk here by opening up this door to let anyone create this singleton class. Cool. So then now going on to our new trend. Our new trend is monostate. So who here has heard of monostate before? Cool. So it's not the most popular one, but we're gonna kind of go through it. So basically, instead of making the object, making the whole class, so that way we're returning a pointer to the class, we're just gonna make every object inside of that class static. So that way there's multiple copies of the class, but each copy of the class carries only one, carries all of its data members and shares all those data members with every other version of the class. Does that make sense to everybody? Cool. So this makes it really easy to end up transitioning from this, we have multiple different objects and transition into a single object. Or like transition from, we now have multiple objects and now we want to split apart that global data. At least we've now kind of started splitting apart the global data a little bit. So it can be a good way to start that transition process. However, it doesn't really replace some of the interface singletons as well because we're trying to access that data once. Cool. So here's what this code looks like. So instead of having this plotter that's an external interface, we're now going to have our plotter be a queue. And so we're going to share that queue with everybody else. And so now we're going to have that queue as a shared object. You could also think of this, a good example would be for holding like X, Y, Z, your parameters, or like your position, velocity, and acceleration. Maybe those are what we hold as our private variables in there. And they're static, so everyone can access those variables in their different copies. But now it's shared amongst everyone. What's everybody's feeling with this? Not the vibe?
I feel like the difficulty I have with this is that with the singleton approach, you're calling get instance, you immediately know like, this is a singleton, I'm dealing with something that like, I should make sure this is thread safe, etc. Whereas with this, it's kind of hidden, right? Like you don't know that there's internal static state when you're calling the plot function.
Yeah. I mean, I would expect that if you built something like this, the methods would be done in a thread safe way. And
I would hope so.
if I saw an API, that's what I would expect. So if it didn't do that, that would be dangerous.
You still haven't improved any testability here, right? I mean, you still have to reset this class between each test if you want to know that you've got it back to some initial state. So you still have to maintain that in unit testing.
Yeah. It is, however, making it a lot harder to see it because you no longer have that get instance where you're accessing that class and everyone knows that it's a class. Everyone knows that it's a singleton. Yeah.
You still have no control over when all those memory variables actually get deconstructed.
So this may be a little bit newer, but who here would rather be using the singleton at this point? Cool. So like definitely comes with its own pros and cons.
It depends on the circumstances, but usually I go with a singleton.
I think in this case, the static would get constructed when you first construct the class plotting.
No, it has static storage duration.
Oh, right.
So program startup and tear down.
Yeah.
Which is different than the get instance version, which I think it's constructed when you first call get instance. That's how that side version works. Yeah.
So it is possible to make a singleton where you can control the structure.
Yeah.
Does this class secretly have an initializer method that you have to call at some point during the function to like set up the appropriate invariants in the class?
Not at the moment. Currently, it's just holding a queue.
In practice, it often would.
Yeah.
Is there any merit to keeping this a class instead of turning it into a namespace?
I mean, maybe not. Like, I think this is really good if you're trying to go from that object-oriented perspective. If you want it to be some shared object and you want it to feel like that class sort of object, maybe this is a good alternative for you compared to just making it a global. But like in general, this is adding a lot of complexity and you may be better off using that global variable instead.
Well, if it's a namespace, you can't pass it around because you can't ever have, you can pass around a class name as a type. You can pass it to things. So if it's generic code, you can say, hey, I take this type T, and if it has this member function, I'm gonna call it, right? But if it's a namespace, you can't do that.
Cool. So we're gonna keep moving forward a little bit. So our next one is dependency injection. So the thing with dependency injection is we've now gotten rid of this global variable that we've been trying to deal with. Now we no longer have the global variable, and we're gonna inject the dependency into each of the objects that use it. So we're gonna end up passing it around and passing it in. And so this is really good because it's reducing our need to have all this testing, but it also comes with its own complexities. So first, a slight little aside. So when I was looking at it and preparing for this talk, I was looking at dependency injection and dependency inversion principle, and I kind of got myself confused. So I'm gonna clarify it to make sure we're all on the same page and understand kind of what's going on between the two. So dependency inversion principle is basically we're gonna eliminate the dependency by adding an interface class. And so by adding the plotter interface, we're no longer dependent on live plotter. So if live plotter changes at all, we aren't worried about that messing with our GPS filter code that's interacting with our interface for our plotter. And this is good because it allows for the testing and mocking that we really want to have. Cool. And then dependency injection is basically we're going to inject our dependency in 3 different ways. So our first way is interface or template parameter injection. So injecting it as in your template. So if you have template, you'll inject it there in that first line. And then setter, that's injecting it into your setter, and then constructor. And so basically we're gonna have one object and we're just going to share it with everybody by passing it around. And so what's interesting with this is dependency injection ends up happening a lot of times through using dependency inversion principle. So we'll do dependency inversion principle first, and then we'll pass that plotter interface to everybody else to avoid having issues if the plotter ends up changing. So in the process of doing all this, we're gonna end up kind of doing both at the same time. But for this, we're gonna talk about dependency injection. Does this make sense to everyone? Cool. So dependency injection. So here's now our dependency injection. So we're gonna have our plotting class, and then in our GPS, our GPS class, we're gonna set it, we're gonna use 3 different ways. So we're gonna pass it in via our constructor, we're gonna pass it in via setter, and then we're gonna pass it in via when we're getting our position, velocity, and acceleration. We're just gonna pass that in. And so this is good because now we've isolated that dependency. We no longer have that global variable that we're calling get instance randomly to. It's really clear. However, now we're adding this to all of our calls. What does everybody think of that?
Can we do composition instead of dependency injection?
What do you mean?
Like have an instance of plotting that lives in the GPS class?
So what was that?
That makes testing hard.
We also still want to hold on to, we still want to have one instance of plotting. And so we're still trying to have our one instance, our global, but we're trying to pass our global in instead of accessing our global randomly. Does that make sense?
Mm-hmm.
Yeah.
We could pass in something like a factory or something like that to basically, or, it could be as simple as a std function that returns the instance you are to use, essentially. But like something that we can use to be able to dynamically, in the test code, we could pass through a function that just passes back the static, like the mock instance versus the actual prod version.
Okay.
That would just help us avoid having to put it on all the functions over and over again.
But we still have to get the plotter in somehow, right?
Well, I guess what I was thinking, I'm imagining a function that returns like the plotting instance that you should use. Like I'm imagining you would pass that as an additional, potentially defaulted parameter for the GPS class.
Okay.
But,
Yeah. Cool. So continuing to kind of move forward. So here's kind of our comparison. So we're going to kind of go through some of the pros and cons of singleton, monostate, and dependency injection. So with singleton, they're really easy to recognize. We can kind of see what they are. And then we're also really easy to access them. If I want to access a singleton, I'm building a new class and I'm like, hey, I want this singleton, I can access it. Or let's say I'm accessing a legacy class, a class that's been around for at least 10 years, has 10 years worth of legacy code on top of it, and I'm trying to access that interface. It's really easy for me to add that singleton in because I can just include the class, call get instance, and like now I'm suddenly adding this new feature, and that's really easy and really fast and really convenient. However, that does come with a risk with testing. It makes it kind of hard for us to be able to use it. Now with Monostate, it's really non-intuitive. It's really hard to see. It's really hard to know, okay, what am I actually changing here? Is this a monostate? Like if I'm looking at code, instinctively I see get instance and I think it's a singleton. If I see monostate, probably not going to immediately go, oh, this is a monostate, this is a shared object. And so we're gonna have to do more things such as labeling our class a little bit different in order to enable us to actually know that this is some magical shared object container, and this increases our likelihood for having bugs and errors. And maybe it's less powerful than a singleton because it doesn't seem to work as well with these interface classes. Cool. And then dependency injection. The nice thing with dependency injection is it gives us explicit access. However, it ends up making it so that way it's really hard to figure out, like, we are having to pass that around everywhere else. Yeah.
And with dependency injection, one of the really big pain points is you've got like a tree or a stack of functions, and one of your leaf ones needs that dependency. Say just plotting or whatever. Mm-hmm. And with singleton, it'd be easy, you just put it in there. Now, like you have to plumb this dependency injection like all the way up the entire call stack, which can be however long it is, right? And then, up at the top, you have like the top level ones have like just, they just take a ton of dependencies because they go down different paths, and every path has potentially a different dependency and different injection, and they've all got to be plumbed up. And then once you've done that, like, oh, I don't need this anymore, I need it for tests or whatever, we didn't do it. You may not always go back up the call stack and clean everything up again, right? Like clean all the parameters, and so you end up with in a state where there's like, you have all these pointer parameters, unused in your function interfaces.
Yeah.
The abstract factory pattern that you mentioned earlier is actually a really good solution to that because you only have one thing you have to pass along.
Interesting. Cool.
Another pro point to dependency injection that I speak to personal experience with is this can actually be a very helpful way to split apart a really nasty legacy code base into nice individual pieces. Like we talk about testing being a really good positive example for dependency injection, but I feel that's more of an instance case of a much broader utility in dependency injection, which is just that now this thing that was global state can now be cut off at the interface level, which means that we can cut it off at the link level, which means that now there's ways to split up pieces of code in composable ways at a bigger level, and I think we're used to thinking about composability with classes and objects and stuff. So that I mean, if you think about it, allocators are dependency injection in action everywhere in the standard library. It's a very useful pattern.
Mm-hmm. Cool. Does anyone else have any other opinions about kind of these three?
I couldn't see all the code on that slide because it was, I was going to say because the code is small, but it's because my eyes are bad, even with my glasses. But it looked like you were passing it along to the constructor and you were storing a reference to it. And you had a couple of other member functions there. Yeah. I couldn't read their names, but it looks like it was being passed there as well. Yeah. And I couldn't figure out why you were passing it to the constructor and holding a reference, and still you were also having those member functions taking the dependency too. Were you trying to simulate the idea that dependencies could just be passed along as in the olden days and as our functional programming counterparts do, just pass it along as a function parameter?
Yeah. So I was trying to show all the different ways you can pass it in. So ideally you'd probably only use one of them. If you're using more than one, you're starting to have some issues.
But once you start holding the references, now you come into really scary lifetime issues. Mm-hmm. Who owns what? how long do they own it, and how long can you guarantee that it's gonna be alive for? And I personally understand the necessity and code basis for that, but I abhor that pattern.
Okay. So ideally, maybe use some sort of smart pointer or something like that to hold it.
Another thing the factory pattern can help solve is the factory maintains the lifetime. You just gotta maintain the factory somewhere in global state. Sure.
So you're, no.
For static, yeah.
Cool. So in a lot.
Or don't, I hate that too. So.
Yeah, I'm a fan of passing things along as function parameters.
Yeah.
So I guess for me, it largely depends on how much this thing makes sense in the context of the interface.
Okay.
If it's something that's a key part of what the functions of the core functionality, then it should be a parameter and definitely not global.
Okay.
But if it's kind of something that's off to the side or done way deep and doesn't make a lot of sense directly in the call, then maybe other methods would be more appropriate.
Okay.
The fact that if you have to capture the dependency internally, the fact that you have to capture the dependency internally to use it later means that your class is doing a bunch of stuff, and it has this dependency on something that's not even associated with it in order to be able to actually do some work, which just seems like a bad design.
Yeah, I mean, I would feel that the constructor or setter method would be basically everything in the class uses this.
Yeah. I mean, look at like a logger. Like everyone in the class uses it, but like how many? I mean, I can tell you right now, our code base, our logger is a singleton. So like that's a really common use case of like where you want that global data and you end up using that singleton instead of using something. But I've also seen it used as dependency injection. So you can kind of go either way. So as we can see with this one, there are pros and cons to kind of each of them. But in a lot of ways, it kind of depends on your use case and if we actually need that global state. If we can get rid of that global state, that's probably the ideal way to go, is to get rid of the global state, rip it out. But if we're stuck with this global object and need to keep the global somewhere, these three are three different ways to do it. However, don't throw the singleton completely into the gutter just because we all don't like singletons. Cool. So now the next one we're going to go into, we're going to jump into SFINAE and concepts. So for our use case, we're trying to create some function requirements. We're trying to make it so that way our functions, we know what's going on when we're doing this template metaprogramming, and we can kind of control what's actually going to happen and where the errors are actually going to occur. So we can say, okay, well, these inputs aren't actually valid. And we can make it so that way it breaks sooner in compile time and breaks a little bit nicer. So it's a little bit easier to read, because if you've read anything like with some template errors, sometimes those are, let me take 5 minutes and let me walk away and come back, and then I still don't understand what's going on. So here's our use case. So we have a function here. This is run a cut of 4, which is basically our way of one way of approximating nonlinear equations. And so what we're doing here is we're going to take, and we're passing in a std function, and we're going to call that function. And with that, we have 3 different things. We have our time, our initial state, and our time step. So we're originally going to do it with doubles. Awesome. You know, we're passing in 1 point. We're trying to figure out what the next x point is. So we're passing in x. We're trying to get like x at a different time. Great. And so we're doing this whole thing in order to calculate it, and then we're going to call it. Cool. So what we're going to do next is, that was awesome, but now I want to pass in a matrix. Now I want to make things a little bit more complicated. I want to be able to pass in more parameters and figure out kind of what's going on for more than just x, maybe x, y, z. And so we're going to pass that in, and now it's starting to get a little bit bigger, and the scope's starting to get a little bit bigger. So our first thought here is, maybe let's make it into a template. Like if we're going to keep doing this, and this is some sort of utility library, like some sort of math utility, we should make it a template. Cool. So now we're going to do this. So we're going to template on time and template on output type. So we want to be able to pass in, time could maybe be an integer. In all reality, we could probably leave it a double, because we're probably not going to pass in time as an integer in this case, but that's okay. And then we're also going to have output type. And so that way we can have a different input output type and figure out kind of what's going on. Does this make sense to everybody? Cool. Cool. So now we're doing that. Now, if you notice here, actually the const expert isn't doing much because we're passing in that std function. However, end of the day, we'd probably templatize it as well. But in this instance, we probably don't need 3 template parameters for this example to make it a little easier for us all to read and understand. Cool. So now, let's say I decided to run it with a double and a std string. So if we go back to our original code, you're going to notice that there are a couple of different constraints that we have to worry about here. So we have this function, and it's calling with time plus time step times 0.5. So our time step has to be, our time and our time step are both units of time. And so those need to be able to be multiplied and added together. So we need to be able to multiply it by a number and add it together. And then we also notice our y0 needs to be able to be multiplied by a time step. So we have to be able to multiply our y0 times some number. So these are kind of our, if we're taking 5 steps back, our constraints that this function has to have in order for us to be able to actually run. So now we're going to break it. Let's say we pass in a double and a std string. Obviously, we can't do anything with the std string. If we go back to our thing, if we pass in the std string, we can actually add a std string to another std string, but we can't multiply a std string times a double. That's not going to work. And so we're going to get this error, and probably not the prettiest error you've ever seen, but you've probably seen a lot worse of an error. Cool. So if you notice, this one actually isn't bad because we can kind of parse through it and go look at it and go, okay, well, there's an issue with the std string and double, and maybe we're doing something weird here, but it's not quite the clearest thing. Cool. And now this is just a pretty basic example, but a good example of kind of where we start to run into these really nasty template metaprogramming errors are when we start using these libraries such as Boost, and we start doing things where it's like, if I don't read the documentation and I do something wrong, I'm going to get a wall of errors that are just compile like template metaprogramming errors just because I didn't read the right things and I didn't send the right things in. Cool. So kind of looking at our timeline here, we're going to look at it and we're going to originally have SFINAE, which was approximately 2002, and then we're going to go to type traits, which were in C++ 11, and then move to concepts, which are C++ 20. Cool. So we're going to look at SFINAE first. So SFINAE is substitution failure is not an error. Now, who here has used SFINAE? Okay, cool. So definitely for me, in the work that I've done, I've noticed SFINAE is something that it's like a lot of times is not worth using just because of the effort it takes to end up doing it. So it's like, might as well just deal with the error somewhere else. And so if we're going to get the compile time error anyways, sometimes it's a lot of work in order to do all those constraints because SFINAE doesn't make it easy for you. So we're going to kind of look at why it doesn't make it easy and how we do things. So basically, we're trying to constrain the template and make sure that it runs only in the ways that we want it to. And it's known for some difficult to read errors and being kind of difficult to constrain. Cool. So here's our original code for SFINAE. We're going to do an enable if on isArithmetic for time. So we want to make sure time is a number. Awesome. So that way we're able to do the multiplication and addition for the number time. Does anyone have any thoughts on this? Pretty simple. Cool. Yeah.
Sorry.
It's okay.
So, pet peeve of mine.
Okay.
So the syntax here, I know this is common because you find this on the internet a lot.
Yeah.
But the type name equals std enable if, that's just a bad pattern to use.
Okay.
Because that doesn't get used at all in overload resolution. If you only ever have one function of that name, then it's a reasonable it's an okay thing to do.
Okay.
But if you ever need to have multiple functions, it doesn't actually get used for that purpose. So what you really, in this particular case, if you're going to do this, and of course it's just my opinion, so I'm not trying to tell you what to do, but the type name equals, if you replaced it with std enable if t whatever is there behind it, like and then comma bool equals true, that'll now be a non-type template parameter,
Okay.
and that will allow you to use it in overload resolution. And so my basic philosophy, whenever you can do something in one of two different ways, and one way kind of works sometimes, and one way always works, I just always do the way that always works.
Okay.
And so in this case, I would say that if you're gonna do the SFINAE like this, that's probably what you should do with the enable if.
Cool.
How
Good.
often do you place the enable if in the return type instead?
Me?
Yeah, or just everyone in the audience, because there's like 3 or 4 different places you can stick that enable if,
Well-
and they all do slightly different things.
The return type was the C++ 03 way.
And that's what we're talking about right now.
Well, but this syntax doesn't even work in C++ 03.
Yeah, maybe with T.
No, yeah, it works.
Other than the underscore, am I seeing an underscore D there?
Yeah.
Underscore T is an underscore.
Yeah.
If those just turned into colons types and colon D, then it's you can have it.
Yeah, you could put that in in where the return is. I think the person who said it wouldn't work was maybe talking about the auto, because that came after C++.
Oh, yeah, there's a lot more stuff in there, yes.
Yeah.
Yeah.
I usually do SFINAE like that when I want to play with overload resolution. Not all the time, but most all the time. If I want to say, no, don't call with a time that is not an arithmetic type, I would put a static assert and tell me exactly the error message that I want my user to read. So I use SFINAE like that when I want to play with the rules of overload resolution the way they I want to play, and not the compiler.
Yeah.
Yeah, so to elaborate on that, if you use SFINAE like this, it works, but it doesn't make the error messages better. It makes them shorter sometimes, but you often lose important information.
Yeah. Cool. So we're going to keep going a little bit here. Cool. So now we're going to try and make it a little bit better. So now we also want to constrain the output type, and we have our 2 kind of things we needed to do. And now probably would do it with the bool. That makes a lot of sense. So thank you for explaining that. But basically what we're going to do here is say output type is either arithmetic or we have a multiply and a plus. Now, in all honesty, I tried to do this originally without using boost and write the SFINAE constraints myself, and definitely went a little bit over my head here. And so it's definitely not as easy as it looks to just like.
Decal type is your friend in these cases.
Okay.
Yeah.
If it makes you feel any better, I don't even know how you would use decal type to make this better. Someone will explain that to me afterward.
Where would you use the decal type?
You just use it in order to put an expression in the place that SFINAE works.
Yeah, decal type instead decal val is, or.
Decal val is absolutely magic.
Is there a rationale behind using 2 of type names instead of sticking all the conditionals under a single?
So time has a lot less condition, or is constrained a little bit more. So time has to be an arithmetic type. It can't just multiply and add, because we can't have a matrix or a vector of times. That doesn't make any sense for this case. We want time to be one value that we end up passing in as our initial time.
Rephrasing the question, why 2 enabled if t's instead of using a single enable if t and using a conditional and expression on those 2 blocks of conditionals? Was there any thought put into that, or?
I'll like combine the 2 type name.
Yeah, into just sticking all the conditionals into a single and enable it.
You definitely could. I just definitely here thought it was like we did part 1 and now we're going to do part 2 and we're going to add part 2 below. Just that way it's a little bit clear kind of the thought process as we're kind of working through this.
You could maybe make the argument it's technically a little bit more readable this way because you're splitting out the requirements in the 2 different types, but they're also combined in the second one anyway, so I guess it doesn't really.
I think the readability argument is good. One thing that hasn't been mentioned yet, and I'm a little surprised, but I think maybe that's because we all know readability is still poor no matter what we do.
Or maybe all of us have seen this too much. It's easy to read now.
I see this in my dreams.
So for sure the readability leaves something to be desired here, but I feel like we've all seen worse.
Well, the compile time
We are in
message
this
is worse. Wasn't the original point of doing all of this is to make the readability of the compile time message slightly better?
Oh, so we're
Cost of the actual code being readable.
so what's up?
Aren't we shifting, we're shifting left to compilation, isn't that the point? Or is it the error messages?
So most of this is the error message. So originally, if we ran this and did have an error, it would still come up in compile time. It would just come up later in compile time, depending on what you're doing. So there's some cases when maybe a double would be valid for us to send in, and it would compile completely, but we didn't want a double. But in this case, if we're sending something that's going to fail, it's probably going to fail at compile time, just later in compile time.
Yeah, I'd say if you're concerned about the readability of it, I'm with Cassio here, that if you're trying to do actual overload resolution, whereas you want more than one of these things to be selected, or if you want to do something like how std optional is all implemented, where you'll get it'll just silently go away, then you use SFINAE for this. If you just want a better error message that it wouldn't work, in this particular case, I would think that just a static assert inside the body would probably accomplish your purpose.
Okay. So now kind of getting into the error message that we've kind of been talking about a little bit. So here it is.
That's not that helpful.
I'm not satisfied.
So
I don't think that's more helpful than the other error message.
it's definitely different.
All the mistakes are there.
Yeah.
To be fair, the compiler could have just said error.
So when I start reading through this, I'll start reading word by word, trying to figure out what's going on. And I hit the things like boost, : binary op detail, : don't care, : value. And I'm like, okay, we've hit a point here where we're kind of falling into a little bit of a pit. So yeah. So maybe this isn't the ideal use case for SFINAE, but we can still use it for some other things. But at the same time, SFINAE isn't making this super easy for us. Yeah.
One thing I was going to say, so the thing is that it is actually nice that it says at least requirement is not satisfied. It's nice that at least, I assume this was built with Clang because I think it's the one that usually does that. But it's at least nice that it gives you that kind of thing, and just, instead of just saying I can't call this function, just don't, that's the end of it. But this is definitely still not super readable. I think everyone would agree with that. But one thing that can be helpful is that if you actually have other code that is dynamically deciding what to call based on the properties of the function that it calls into, this can still be helpful, because the problem is that otherwise, if the template is completely unconstrained, it'll end up deciding that it can do it, and then that's when you start getting really deeply nested instantiation context errors where something chooses the wrong overload, and then it really gets hard to diagnose. So it can still be useful to just have this say stop and don't move forward. But yeah.
Okay. Thank you. So now we're going to go into concepts. Now, so moving into concepts, who here is working in a C++20 code base? Just trying to see. Okay. So
Could you do that again? Because I'm interested in this answer too.
who's in a 20 code base?
Somebody wants
So that's 15% maybe?
Yeah.
Okay.
Okay, cool. So concepts came out in C++20. So keep that in mind if you're not in a C++20 code base. I'm sorry, you're going to have to go back to SFINAE, and good luck. But with that, basically we're trying to create these compile time constraints, make them a little bit more readable, and make it so that way we have these name sensitive requirements. Cool. So let's go make our constraints now and make it do the same thing as SFINAE. And so first, we need our arithmetic constraint for time. It's the first thing we did last time, it's the first thing we'll do this time. So if you notice, we're creating this concept called arithmetic, and it's going to be integral or floating point, because we can take an int and we can also take a double as time. Probably won't take an int, but you can. And so we're gonna OR those two together, and then we're gonna pass it in. Cool. And this looks a little bit easier, in my opinion, to read than SFINAE was. Does everyone kind of agree with that?
Totally.
Okay. Cool. And so now we're going to continue and do our add multiply weirdness with this matrix. And so how we're going to do it is we're going to require that we have our class and then our num. So we want to make sure that we can add to, we can multiply by a number, and we can add two different of this matrix or double together. And so those are kind of our constraints on it. And so that's how we're going to do that. And then we're going to require add and multiply with output type and time. So we have to be able to have output type add together and then output type be multiplied by time. Does this make sense to everybody? Cool. Does anyone have any critiques on this at this moment? Cool. So now let's look at these error messages because we've been kind of on this track of trying to figure out these compile time error messages. So this is what we're going to get. So, does this feel a lot better?
It does actually give you the specific problem.
Yeah.
Well,
And it tells you in the last thing that
Yeah.
it's code next to you can like see it.
it doesn't tell you. Okay, no, it does tell you which concept failed.
Yeah.
It would be nice if it told you to fix, if it could figure that out. But maybe that's a bit helpful. Maybe not.
Yeah.
So is that what the answer?
There is a, I'm sorry.
Okay.
That's the thing. It's all.
Cool. So this is definitely feeling a little bit better, a little bit easier to chew. If you're going to put someone who hasn't written a ton of template metaprogram code in front of this, they're probably going to be able to get through it and fix it themselves and ask a lot less questions than putting them in front of the ones we've seen previously. Cool. So with that, kind of our comparison. So we have SFINAE. It has a little bit harder to read error messages. It's kind of difficult to make those complicated checks. And it also is a little bit harder to read. Like I can't read a SFINAE, like something that's the SFINAE check and have it be, oh, this is obviously what we're checking here. And like I can parse through that like pretty instantaneously. Versus concepts, you can do that really instantaneously and we can make those custom checks. However, with that, concepts are C++ 20, and so that does limit a lot of people who haven't quite migrated yet. Cool. Cool. So let's move on to our next one. So our next is polymorphism. Cool. So for our use case, we have one interface with multiple different implementations. This is kind of your key object-oriented design implementation. So we're going to have our base network connection class, and then we're going to have a TCP class and a UDP class. And both of those are going to go up through the base network connection class and use some of the functions associated with them. Now, really quick, I'm sure everyone has, but has anyone not seen this sort of polymorphism sort of thing? Cool. So here's kind of our timeline. So we have our virtual functions, and then we're going to move into CRTP. And then in C++ 23, we get deducing this. Cool. So for virtual functions, this is runtime polymorphism, and it's kind of your quintessential how we do object-oriented. If you go into a older style code base, a code base with a lot of legacy code, this is what people reach to first. This is your first thing is I'm going to mark it as virtual. I'm going to have this whole tree, and this is how it's going to look. And it's kind of quintessentially overused. So with that, here's kind of what the code ends up looking like. So here we're going to do we're going to have a abstract base class, and that's going to have a pure virtual function that's initializing our configuration. And then TCP is going to override that function, and so is UDP. So with that, that does come at the cost with the vtable, as well as in this instance, we probably, with the little information we have, maybe it doesn't need to be runtime, maybe it does need to be runtime, but it's not exactly it doesn't give people today the warm fuzzies. Cool. So now we're going to go into CRTP. And so with CRTP, we're getting compile time polymorphism, and we're basically going to force a downcast from the parent in order to access the child's elements. Cool. So here's how CRTP works. So we're going to have this init function. And basically what we're going to do is we're going to static cast down to the child's data and then call that function from them. And so each child's going to have an initialized config function. And in the parent class, if you call init, it'll call the child's initialized config. Does this make sense to everybody? Cool. How does this feel for everybody?
like I've done it 1,000 times.
Okay.
I like CRTP a lot. I think the biggest issue is that you don't have like, it's hard to tell if you're actually overriding the function you think you're overriding. You could just be creating a new function in one of the derived classes. There's no like override keyword or anything like that. So a lot of times you'll be like, well, why isn't this function being called? And it's like, oh, I'm not actually. I'm casting to, there's no override in the child class. So that's kind of a pain in the butt.
It's also not super apparent in that side of like, you can't just look at a class and go, oh, that obviously has that virtual or override, like that's what's going on. Cool. So now we're gonna get into deducing this, and this is a C++ 23 feature, and it simplifies some of our compile time polymorphism. So with that, we're gonna have the same sort of thing, however, we're gonna pass in this ampersand self, and that basically will move it so that way we're now getting the child pointer, and then we're gonna call that initialize config. Does this kind of make sense to everybody?
No.
Yeah.
Okay.
This is the first time I'm seeing deducing this like in action. So
Okay.
this is new information.
It's so unintuitive.
Yeah, so it's very much different. But so basically self is going to be the pointer of the child object. So we aren't doing the cast like we did in, if we jump back 2 sides, we have the static cast derived. We're kind of doing something similar, but we're doing it in the initial as an input. So you can think of it as we're calling yourself as the first parameter in. Does that kind of help at all? I'm guessing not.
Self is of like the static type that is like, so you would be calling this on like a derived object, and like self is going to be the static type of the object you're calling it on. So in this case here, self is going to be deduced to be either TCP or UDP.
What is the cost of doing this?
What is the cost of doing
Yeah.
it?
This is compile time.
Yeah,
So-
new syntax.
So compile time.
Yeah.
Nothing.
So
Compile time.
Well,
Nothing at runtime.
there's already, even in the previous implementation where init had no parameters, there was already the implicit this as the first function parameter anyway. So.
Right, but it was of the higher static type, of the parent static type.
Yeah, so like this
Correct.
this is still using static information at compile time, like it's based off of the static type at the call site.
So what happens when the compiler can't figure out the actual type when it's being called? It's always passing in the static
I
type
believe
that
it's
you're
always
already
the
on.
static
Yeah.
type.
So if the actual like dynamic type is actually lower
Yeah.
than that,
We'll get
we're
there in
only
a
calling
second.
at like the middle of the tree.
If that's my understanding, yeah.
Cool. Are we cool to keep going?
Yeah.
Okay. No, it's cool. Thank you for explaining it. Cool. So we're gonna keep trekking through. So now, of course, I think of inheritance and I go, I want to do some multiple levels of inheritance. I want to do all the things with this. And so first we're going to do that with virtual. And that's super easy. And I include the Godbolt links in case you're trying to figure out like what I did. But so we're going to go through and have our top one. And so we're just going to inherit from it. And now I'm not pulling any tricks here, but take a look at it and see in our int main, so A and B, which for session B, what is it going to output? Like which one's going to call? Is it going to call, yeah. Is it going to call session or TCP? And I'm not playing any tricks here, so don't expect me to be pulling something sneaky. So everyone who thinks it's session A, raise their hand. Or sorry, thinks it's TCP, raise their hand. Okay, everyone who thinks it's session, raise their hand. Cool. So, yep, so it outputs session as the second one. So exactly what we'd expect with our virtual inheritance. It's kind of going up the tree, it's working really nice. So now let's get into CRTP. So if you notice it, we're gonna do the exact same thing that we did before. Cool. Can I get some, what's up? So can I get some thumbs up when everyone thinks they're ready? Okay. I think we're gonna do our poll now. So who thinks TCP is what outputs here? Cool. Who thinks sessions what outputs here? Okay. So TCP is what outputs here because it's accessing the derived. So it's the templated on derived, and derived is TCP. And so we're having this multiple levels of interesting inheritance. And so it's not quite as clear as I personally would like it to be, and it gets kind of nasty really quickly.
Yeah, I mean, it kind of looks like TCP is designed to make this work correctly, but it doesn't use it in a way that makes it work.
So you can do really interesting things with it, though, of like accessing different ones. However, it doesn't do our virtual polymorphism as nice as we'd like it to.
Right, I mean, you could make this work by having TCP implemented to check whether T is void and pass, and determine whether to pass T or itself to the parent.
Okay.
Which, based on how it's used, looks like that's what it's intended to do.
Yeah, for sure.
But then what if the child doesn't have an initialized config function?
Then it will go back to the parent because
Well, you
because
have
it's
to have
inherited.
logic in TCP.
But because session inherits from TCP, so that means it has an initialized config.
Oh, that's true. That's true.
If it doesn't define its own.
Cool. So let's go to the next one. So this is deducing this. If you notice, deducing this does clean up a lot of the template stuff that we had with CRTP, so it's a little bit easier to read. And we just have the mysterious self going on here. And if you know what's kind of going on there, it kind of cleans up everything a little bit. So take a look and then figure out if session or TCP is what'll be outputted. Okay. So everyone ready? Cool. So who thinks TCP will be outputted? Okay. Who thinks self will be or session will be outputted? Oh no. Okay, cool. So yeah, session will be outputted here. Yeah, it does exactly what we'd expect it to. Kind of goes down. And so we're doing this same polymorphism that we'd expect to do. It's pretty elegant, it's pretty nice, and that's making it a little bit easier. Cool. So here's kind of our comparison. So we're doing runtime polymorphism with the virtual, and it's really easy to read and trace kind of through with CRTP. We're doing compile time polymorphism. However, we are adding all the levels of template, and if that's not something you've seen before, it can be kind of hard to read. And now everyone here, I'm sure, has seen it a decent chunk of time, so it's a lot easier for you to go, that's what's going on here. But if you're looking at someone who hasn't, it's a little bit harder, and it makes that multi-level polymorphism a little bit difficult. And then deducing this has compile time polymorphism. However, it is a C++23 feature, and we are still having that difficulty to trace. Cool. And then the last one we're going to go through is design methodology. So here's kind of how I see potentially our flow of design methods. So we're going to have, starting with procedural, kind of your C style, we're going to do A, then B, then C. And then we switch into, we have our object-oriented programming and our functional programming. And now functional kind of started before procedural. There's a little bit of ambiguity there. But at this point in time, it kind of feels like they're both working next to each other. And then the next thing's data-oriented design. Cool. So now we're going to look at design and evolution of C++ by BRNA and try and figure out kind of what we're trying to get to with C++ and kind of what the design of C++ was for these design methodologies. So if you notice here, there's a couple of interesting things. First, it's trying to support C++ was designed to support object-oriented programming. Now that doesn't mean it is object-oriented because it has supports. It's not just an object-oriented language. However, what's interesting here is that it is a key tenet is trying to support those features. And it's also supporting generic programming. Cool. And then the design rules, also from design and evolution. So kind of some of the interesting ones are that we want to have this idea of having like it's not going to be everything, but also we want it to have support for every style. So we have styles such as functional programming, where we still have some pieces of functional that aren't as easy to do in the language currently. And so we have this interesting kind of thing of like C++ having a variety of different design methodologies and us trying to deal with all of them. And some of them are older and some of them are newer. And some of them are older in like implementation of like we use them more often today, or we use them more often in the past. Cool. So here's kind of our example problem space. So we have packets, and we're going to try and extract all these time packets that are coming in, let's say, from a spacecraft. And we want to be able to extract all of them, and we have instantaneous and long-term events, and figure out which ones happened during this talk. So first, we're going to look at procedural programming. So this is kind of our original programming style. Think more C than C++. We're going to do A, then do B, then do C. Think like a recipe. We're going to follow it kind of verbatim, kind of going down the list. So code-wise, this looks a lot more like this. So we're still going to have our functions, but we're going to originally get our telemetry, and then we're going to filter our telemetry. So we're going to do the first thing, and then we're going to do the second thing. And then the second thing, inside of filter telemetry, we're going to loop through, and we're going to go through each telemetry point, be like, okay, here's the first telemetry point. Is it a duration event? No. Okay, since it's not a duration event, is the time within? And then we're going to add that and return it. Cool. And then now we're going to go into object-oriented. So object-oriented originally started with a pattern language, which was pre-C++, but the idea being we have buildings, and buildings end up having a lot of characteristics in common. And so what we're going to do is we're going to look at all of that as a whole and try and understand kind of what's happening. And so noticing that some buildings end up all being the same and having this cookie cutter aspects that we can just apply to different areas. And so then this ended up migrating into design patterns by the Gang of Four, where they came up with a list of different patterns that they noticed being implemented across different object-oriented programming and different patterns that we can use throughout our code to enable us to do things better. Cool. So here's kind of a list of some of our common object-oriented patterns. If you notice, there's a lot of them. And one of the interesting things with all these patterns is there are some that are very similar to each other. So you have a lot of things where it's like, wow, this is similar to this other thing. And so when we're looking at it, it can be kind of hard to figure out, well, what's really the difference between these two? Like, is there a lot of difference here, or are we just making it work? Cool. So here's kind of our object-oriented. So what we're going to do is we're going to have our get telemetry, and then we're going to have a class that we're going to end up storing passing our telemetry into and creating a filter class. And in that filter class, then we can now call our filter class and get the filter telemetry. So we're adding this kind of external jump around. And you notice that a lot with object-oriented, when we're working in an object-oriented code base, everything becomes a class, and every class has stuff inside of it that we're going to end up modifying through and passing these really large classes around. And that can be kind of difficult to figure out kind of what's going on. And then now we have functional programming. So functional programming kind of started in like 1930s, was kind of the original foundation of where functional programming came from. And then it's now used in languages such as Lisp and Haskell. However, C++ also has a lot of those capabilities. So with that, there are kind of three functional patterns that we can think of: functors, monads, and applicatives. And what's interesting with this, and what I noticed, is that functional programming is to functions what object-oriented is to classes. So we're basically just kind of trying to create these patterns and use them for functions, just like we did with classes, just there's a lot less of them. So here's kind of a really simple example of a functional program. If you notice, we're going to have our filter, and then we're going to pass it into a copy if, and we're going to kind of do this all functionally. Now it looks a little bit different from our object-oriented because we aren't having that additional class. Cool. And then now getting into data-oriented design. So data-oriented design came up in 2009 and is originally when the term seems like it came about. And basically what we're doing is it started with game developers working in OO. The idea being, okay, we have a grass class, we have a bike class, we have all these different classes because in OO you kind of wrap your head around the different objects that you have and can associate it with something. However, that doesn't lead well to performance. And so in game development, when you're worried about that low latency, suddenly it becomes we need to figure out how to deal with that low latency and figure out how to make it a little bit better. And so this is where they started to move away from object-oriented, try and figure out how to get that performance. So they did that by basically, instead of we're worried about cache, we're worrying about making sure things are local, the localities are with each other. So instead of putting all of our telemetry into one giant vector and having to parse through the vector, we're gonna split it into 2 vectors and reduce that if statement. And so we're calling 2 different functions to process that data, which will then make it a little bit more performant. Cool. Cool. So now we're gonna jump into some pros and cons. So with procedural, it's really simplistic. It's definitely like our older style, kind of original sort of work. And it's really verbose. You look at it and you know exactly what's going on here. Object-oriented is kind of colloquially overused, is a little bit difficult to read through and parse. And however, it's really nice to look at the data. So we look at the data and we know exactly what's going on. We can kind of parse through it and we go, oh, that's a grass class. That's what's going on there. However, it's really easy to start adding stuff to that grass class and expanding its scope. And it's really prone to a lot of anti-patterns. So it has the patterns that are really awesome, but it also has the anti-patterns that are not so awesome. And from Tony's talk this morning, your objects are made of Velcro. So we kind of have this ability to just keep creating all these objects and just keep adding stuff into them and have it be okay. And then functional, we have these pure functions and this ability to have this immutable data. So we're kind of moving our kind of mind process a little bit and dealing with it a little bit differently. And we're able to treat our functions as our data. And so that's really beneficial. And then data-oriented ends up being a little bit more performance mindset, a little bit backwards to how we thought about things with object-oriented and functional. But like when you look at all 4 of these, end of the day, none of them are like the end-all be-all. Like we can't just use one and have it work for everything. We've done that with object-oriented. Like how many code bases are just 100% object-oriented and that doesn't quite work. That doesn't do what we need it to do. And so when we're using a function, we tend to need all 4 of these in little pieces and parts and when creating a large code base. Cool. Does anyone have any thoughts about this? Yeah.
So I know I tend to start by making things procedural, as simple as good, and then start switching things out as I need to reuse pieces.
I'll find that I'll start procedural, and then I'll make an object, and then I'll start realizing that my calculations don't need to belong in an object, and then I start pulling the functions out.
Yeah.
So maybe this is more like an evolution instead of just like an instantaneous, like today we make everything objects. It's we start with one thing and then we're gonna start evolutionizing within our own code base within like a week or so while we're trying to work on an issue. Yeah.
I like functional programming because I find it very easy to test.
Okay.
Because there are really well-defined inputs and outputs.
So the point you just made about the evolution, you know, I've actually had a couple of the more inexperienced developers at my work in the last week say, you know, I started writing something, I felt like, well, I wrote it procedurally and I thought that was wrong. You know, like, okay, that was just me throwing something down. Now I need to OO this up and stuff. So I think there's actually this mindset to some degree that you need to move it towards OO if it's going to be production level, you know, which I think is interesting that maybe for a while that was a mindset that has shifted a bit.
Yeah.
So are we potentially conflating a couple things here when we talk about object-oriented?
Yeah.
Because I recall back in the day there was a distinction between object-based and object-oriented. Object-based being the idea that one encapsulates data in objects and maintains class invariance pre and post conditions. And object-oriented was a little extra to allow for dynamic polymorphism through virtual functions.
Okay.
In my mind, there's kind of a distinction there.
Okay.
And also, you can look at cases where it makes sense to encapsulate data inside of classes or structs and either maintain their invariance or just wrap them in structs when there are no invariants to be maintained, like complex numbers or points, right? There's not necessarily need to have getters and setters for simple structs, but the idea of the object-based programming of keeping things together that belong together is a very useful and powerful technique. And let's not throw the baby away with the bathwater by saying, that's object-oriented, it's not good, right? It's a matter of degree and looking at what's the best solution for your problem, in my humble experience.
And I remember reading somewhere from one of the functional people, kind of to that point, I forget exactly what it was or where I found this, but it was something along the lines of like the zen of the function is realizing that functions and objects are the same thing in a lot of ways. A function, in the sense that once you sort of expand the definition of function to like what we would think of a closure or a lambda, those are kind of just different ways of looking at the same thing. Some data that has some behaviors that are like a function that we can run on. And I thought that's a very interesting perspective for like, we often draw pretty hard lines between these two styles. A lot of the times because of that history, right, that you highlighted on this, like where these ideas came from. But you know, I think we end up talking about these two styles as a form of like what's better for this type of problem when maybe the language's ability to express those styles is the limiting factor more, and its opinions about how hard that line is drawn between the two styles. I mean, in a lot of ways, we talk about procedural programming as if it's its own thing, not like really often discussing that object-oriented programming languages often are implementing their objects with procedural functions, like, or like if you think of like a generic programming with the STL, like in a lot of ways that's like passing functions and iterators around the different things, right? Like you can argue that's a slightly more functional style than it is. They're certainly not object-oriented. And data-oriented is not something I have a lot of opinions about, but again, it's about performance, right? Like,
yeah.
There's a certain type of performance that those developers care about, and like that's a set of patterns and styles that help them. They want a language that can express that better than what we think of an object-oriented language. I really don't see hard lines between all of these three categories or these four categories in ways that I think we often frame them.
Yeah.
So when you started this section, I promised myself I was just going to stay out of this. I have very strongly formed opinions in this realm that probably disagree with a lot of other people. But what you have, but this talk and the previous one and even part of the previous one has basically convinced me that I'm going to change. I'm going to rewrite a portion of my talk on Thursday to address some of these issues. But it's from actually I think somebody up front made a comment that I like functional because it's easy to test. Actually, that's what original object-oriented programming was supposed to be. And what you're saying is object-oriented programming, when it's done right, it's very hard to distinguish from functional programming. I mean, it really is from a high-level view, especially from a testability viewpoint. The problem that we have, and the reason we have dependency injection and a lot of these other patterns that have had to be invented was because we, as an industry, we do object-oriented programming wrong. We just do it wrong. And the patterns that we've developed from the beginning, they're not, I mean, go look at anything that Alan Kay has said, who invented object-oriented programming, about what object-oriented programming is about. We focus on objects. We focus on, and that's not what object-oriented programming is about at all. Well, why did he name it that way? He said he really wishes he didn't. But anyway, I think that what you're saying is true as well, and that there really are, when you step back and look, you try and look at them from a perspective of what is the interface and what is the implementation requirements upon them. I think a lot of times we end up focusing on implementation requirements and we miss the forest for the trees. And when you do object-oriented programming right, it really does feel like functional programming, especially from the standpoint of inputs and outputs and testability. It's extremely testable.
I think what that comment highlights is that the term object-oriented programming is about as overloaded as safety in C++, and that it deserves quite a lot of scrutiny when used in discussions.
Yeah, and And I think when you write code well, like regardless of which paradigms you use, it becomes easier to test. Like certain patterns are easier to or more prone to anti-patterns than others. So I guess that's what I was more talking about when I said functional was easy to test. Obviously, if you do OOP correctly, it's not difficult to test.
Cool. So kind of drilling back down to the point of this talk really quick. We've kind of circled around it. It's the idea that like the new thing isn't always the best thing. Like we are dealing with a lot of trade-offs here. And end of the day, like no matter which one you do, you're going to end up reaching the same goal. And like we can take really great things from each one of these. Each one of these has aspects that we should use in our own code bases. Like when I was looking at the code base that I use at work, it's like we aren't using purely one of them. And so trying to figure out an example where it's like, oh, I can twist this to just be like functional or just be procedural or just be data oriented or just be object oriented is really difficult because we've started to hit this point where we use all these different paradigms and kind of mix them all together to come up with something that's a little bit better because we're able to do that and we're able to mix it. And we have a language that enables us to use all these paradigms to create something that is useful for us and is readable and usable and testable. You had something to say? Someone?
I was just gonna let you go and
Okay.
finish your talk. I was just gonna say that at a base level, some fractions of object-oriented programming and functional programming are fundamentally identical because before we had functors and before we had line, the way that we would do functional programming is that you would hand spin a functor. We just have the class that has the name of the thing and your bound variables, or you put your binding or your member variables that get passed into the constructor. And you'd have an operator that would have your unbound variables, and that was a functor, and that was done in a style that I think most of us would recognize as object-oriented. So at some level, at least those two are, for some applications are literally identical.
Mm-hmm.
But not a functional programming functor. That's different.
I don't think so.
Maybe someone has better comment.
Cool. Really quick, what do you have?
Yeah, I guess one of the breakdowns for me is like across those things is I see like, I kind of like lump the other twos together in that they're more like values, and object-oriented program is more about identity in that like, like different, your different pointers are interchangeable, right? Like stuff has an identity that it preserves, and that can be useful or that can be very harmful, or can be very entangling. Whereas the other ones, like like an integer, like you pass an integer, you pass a hash map, you don't care about, you care what's in it, but you don't care like the identity of it.
But with data oriented, you care a lot about the identity on
or
the same
location,
side.
But like how it's laid out. But like one thing is what it is. Like you're just dealing with data, right? You just want it efficiently stored or packed.
Cool. So end of the day, we have these four, and they are all, we need pieces and parts of all of them, and we can learn a lot from looking at it and looking at these legacy code bases that use object-oriented patterns or use our functional patterns as well as using procedural. We can learn a lot from looking at some of those very old styles of code as well as looking at the modern code and trying to figure out what's going on and understand what's going on and figure out what sort of code we should be writing when we write our code bases. So like maybe when we're looking at our code base, we shouldn't keep sticking to the same paradigms we've used before, but understand, hey, maybe there are other things that are better or more useful or can allow us to get more readability and get all the abilities and get the things to be a little bit better. Cool. So now we're gonna look at a couple other potential evaluations. Just kind of bring them up so that way there's a lot of different things that newer isn't always better with. So our first one is union versus variant. If we were to take a guess here, probably variant is better than union. Up next, we have enum versus enum class. There's still a lot of really nice things you can do with enum that you can't do with enum class. And so there are pros and cons with that, and there are cases where both are still needing to be used today. We also have raw pointers versus references versus smart pointers. And so this is one of those where I don't know, in modern code bases, you still have cases of raw pointers being moved around. And so we still do have these older patterns being used today. And so, we could sit and evaluate, is that the right call? Is that the wrong call? Okay. We also have raw iterators versus some of the standard algorithms. And then we have C-style casts versus what I like to call fancy casts, because I think they're a step up. They're a little bit fancy. And so those are your static cast, dynamic cast, reinterpret cast, and const cast. And then we also have allocators versus PMR, and printf versus cout versus lib format. Cool. So in conclusion, the big idea is that newer isn't always better, and that we should take and apply the same amount of scrutiny to the code that we wrote 20 years ago as the code we're writing today, and figuring out, hey, is this new thing that just got added to the standard or just got talked about in some conference talk, is that really the new hot thing we need to use everywhere? Or do we need to apply the same amount of scrutiny to it as the stuff we've been using for 20 years? And so kind of taking a look at that and figuring out how to avoid either using the great new thing because it's new, or keeping on using the old thing because it's old and we've tested it and it's amazing. And so kind of trying to figure out how to bridge that gap and be able to do both. So end of the day, our use case ends up determining our usability and determining what we're able to do. Are there any questions?
First of all, we got a clap for you.
Okay. Thank you.
When you were looking at this, was there anything that you were like, that was a mistake right there? Like, obviously not better, but newer.
I definitely ran into that like last week. So I went into the case where I was like, ooh, look, it's a stood pair. And I just used it in a couple of different places because it made things really nice. And I had to take a step back, and we talked about it, and it was like, oh, maybe stood pair wasn't the right option to use here, but it's a lot of like where you were using it and why made it potentially worth it. However, a lot of it became maybe the constraints that were on the system weren't right. And so we needed to organize the code a little bit differently to eliminate some of that. But yeah, I also came from a very OO background, and so it was interesting to see kind of the things that have evolved, and like there are areas where that's really nice, and there are areas where it's like, wow, there are some of these other patterns. Does that answer your question?
Yeah. Eric's definitely had code reviews from me where he's like, don't use a stood pair, use a struct. And I'm like, good call.
Core guidelines.
Yeah.
Cool. Are there any other questions? Cool. Thank you so much.